Gravitation and Black Holes. Gravitation and Black Holes for everybody in 5 hours. Hello, welcome to this short introductory course on gravitation and black holes. My name is Walter Urbaniak. I'm a retired computer networking engineer. I have an interest in physics, but I am not a physicist and not a professor. This is a 5-hour introduction to gravitation and black holes. This class is targeted at persons who are not physicists, but have an interest in physics or just the science fiction of black holes. Gravitation, weight, acceleration, orbits, and tidal forces on Earth, the planets, and stars. Why are there 2 high tides and low tides per day? How to rocket to Mars. Einstein's general relativity as applied to planets, stars, and black holes. Curved spacetime, gravitational redshift. Could you survive entering a black hole event horizon, or would it kill you, and how? Time travel to the future by orbiting a black hole. We will not cover the Big Bang and expansion of the universe. The transcript for these lectures is available as a PDF. The link is available in the description of the YouTube video. The course is divided into 5 one-hour videos and 6 supplementary videos. The main course material is divided into 29 sections. After any section, you could pause and resume at a later time. In the description of the video, you can jump to any section you wish. I will read out the roadmap for the course. Skip if you wish. The time for each section is given in minutes, but I will not read out these times. Introduction and approach, gravitational force and acceleration, falling from the Leaning Tower of Pisa, weight, Schwarzchild radius, black holes, supermassive black holes, quasars, human shell observer, general relativity, Schwarzchild solution, time dilation, gravitational redshift, spacetime curvature, plunging into a black hole, tidal force and acceleration, tidal ouch, death, and spaghettification, circular orbits and time dilation, gravitational waves and merging black holes, rotating black holes, accretion disks, jets, and quasars, light, part 1, radial for non-rotating black holes, light trajectories for non-rotating black holes, gravitational lensing, wormholes, dark matter, artificial gravity, warp drive and faster than light travel, and anti-gravity and dark energy. Some of this material will be new to you and possibly confusing. Don't worry about following every detail of things that are completely new to you. You will learn some new concepts and terms and get some understanding of one level of the reality of our universe. We will cover more about black holes than many physics professors might know. I am not an expert. This information comes from reading an ebook freely available on the internet and from Wikipedia articles. I have done many calculations to produce this course. I verified results where I could, but I apologize for any errors. I will give attributions for images in the lecture script file. Introduction and approach. I'm holding a ball in front of my face. It is not moving. I let it go, and it falls. No surprise there. Its speed increases as it falls. It accelerates downward. Why does the ball fall? And how does the ball fall? Around 350 BC, Aristotle said that the natural motion of the ball in air is to fall, and that heavier objects fall faster than lighter objects. Aristotle's explanation sufficed for about 1900 years. Building upon Galileo's earlier work around 1590, Isaac Newton produced the physics of motion in 1666 and his law of universal gravitation after that. The mass of the ball and the mass of the earth exert a mutual attractive force on one another. When I release my grip, the downward force on the ball's mass causes the mass to accelerate downward toward the center of the earth, and causes the earth to accelerate very slightly toward the ball. Newton's explanation, which also explained the moon's orbit around the earth and the earth's orbit around the sun, reigned absolutely for about 250 years. Then, in 1915, Albert Einstein determined that gravitation in the universe is actually better described by his theory of general relativity. Why does the ball fall? The mass of the Earth deforms the fabric of spacetime and causes it to curve. We will learn later what this means in the vicinity of the Earth. When I release my grip on the ball, the natural motion directed by the curved spacetime near the Earth is for the ball to accelerate downward toward the center of the Earth. This sounds like either a return to Aristotle or a meaningless gobbledygook, but it correctly predicts and explains new phenomena such as black holes and the expansion of the universe since the Big Bang. In this course, we will get a gentle introduction to black holes and curved spacetime. Our approach will be to derive the formula for some gravity-related quantity using Newton's classical mechanics and law of universal gravitation. Then calculate the value here on Earth. Then compare the values on other planets of the solar system. Then compare the classical values for the Sun, some other stars, and some black holes. If the values need to be refined due to general relativity, we will look at the updated values and formulas to see the effects of general relativity. But we will not derive the correct general relativity formulas, which would require a much longer and more mathematical course. We will also determine how close a person could get to a black hole and survive. The first hour of the course might seem slow, but later we will get to black holes after we are oriented. So let's begin. Gravitational force and acceleration. Around 1666, while quarantined away from university due to the plague pandemic, Newton invented calculus and the physics of motion, forces, and acceleration. He identified that the gravitational force between two masses that are either point sources or spherically symmetrical mass distributions is always mutual, each to the other, attractive, directed along the lines of their centers, directly proportional to the product of the masses, and inversely proportional to the square of the distance between their centers. Force is proportional to the product of the masses divided by the distance between centers squared. Larger distance produces smaller force. With the masses in kilograms and the distance in meters, the force is in newtons, kilogram meter per second squared. We can think of Newton's gravitational constant, capital G, as the conversion to a given unit of force. Newton's law of universal gravitation and the value for g, 6.6743 by 10 to the minus 11 meter cubed per kilogram second squared, are universal for an apple dropping from a tree, the trajectory of a cannonball, the moon orbiting the Earth orbiting the sun, and a planet orbiting a star in some distant galaxy billions of years ago. Even antimatter responds normally to gravity. Gravity does not become anti-gravity. But Newtonian gravity is not quite right close to a black hole. Newton's second law is that net force equals mass times acceleration, F equals ma. Mass times vector acceleration equals the vector sum of the forces on the body. Or vector acceleration equals the vector sum of the forces on the body divided by the body's mass. Physicists have verified that inertial mass in F equals ma and gravitational mass in Newton's law of universal gravitation are identical regardless of material and quantity. This is an assumption of Einstein's general relativity, whose predictions have been verified many times and never contradicted. For two bodies and only the gravitational force, we ignore air resistance for now, we get the following freefall accelerations. The gravitational acceleration of each body depends only on the mass of the other body. The acceleration of this blue sphere depends on the mass of the green sphere. The acceleration of the green sphere depends on the mass of the blue sphere. For dropping a ball at the Earth's surface, the acceleration of the ball is significant, but the acceleration of the Earth toward that ball is not, and so we treat the Earth as stationary. Dropping a heavy ball and a lighter ball at the Earth's surface, the acceleration of each ball will be the same, independent of each ball's mass, dependent only on the Earth's mass, when we can ignore air resistance. Galileo believed this would be the case, and Newton confirmed this. But if we were to drop a feather, we would be wrong to ignore air resistance. The feather would be greatly retarded by air resistance, unless we drop it inside a vacuum column or drop it on the moon, as an Apollo 15 astronaut showed. I want to give some information about Galileo here, but to keep the class moving, I will provide this as an 8-minute supplementary video. There are 6 supplementary videos. The Earth is not a perfect sphere with perfectly spherically symmetrical mass distribution. It is squished at the poles and bulges at the equator. It has oceans and continents, oceanic trenches and mountains. It's close enough to ideal for this class. However, to do precision landings on the moon more accurately than the Apollo missions, future moon missions need to use an accurate gravity map of the moon, not the spherical idealization. Let's consider a low-mass object at or near the surface of a spherically symmetrical planet, moon, or star with large mass, capital M, and radius, capital R. The surface gravitational acceleration lowercase g equals uppercase G uppercase M divided by uppercase R squared. At Earth's surface, if we plug in these values, lowercase g is 9.81 meter per second squared, or 32.2 feet per second squared, and this is always called 1g. This is the downward acceleration that an object experiences in the absence of any other forces, such as air resistance and contact forces. Planets with more mass than Earth might have larger or smaller surface gravitational acceleration than Earth, depending on their radius. We will see this shortly. Planets and stars do not have uniform density. They are denser at their cores and least dense at their surfaces. However, to compare planets, it will be useful for us to consider the average density for a planet or star, being its mass divided by its volume. Its density at its core will be denser than its average density, and its density at its surface will be less dense than its average density. Volume is 4/3 pi r cubed. We can calculate the average density as mass divided by volume. We can then flip that around and calculate mass from volume and density. And we can calculate g for that object in terms of density and radius. And we get that surface gravitational acceleration is proportional to average density times radius. We will use this to compare different planets and stars because densities and radii are easier to have some feel for and compare than masses. The Earth's average density is about 5.5 times the density of water, higher than the density of the rocky mantle and less than the density of the iron core. The Earth has the highest average density of all planets in the solar system, though Mercury and Venus are nearly as dense. You know the expression to walk before we run. Well, in this course, we're going to fall gravitationally before we stand against gravity. Then we will learn about standing near a black hole, plunging into a black hole, and orbiting a black hole. We will start out slow. Let's look at acceleration and falling over a short distance. If an object is initially restrained at rest and then released and falls for t seconds, its instantaneous downward velocity, speed, at time t will be velocity equals g times t. Near Earth's surface, that g will be 9.81 meter per second squared, or 32.2 feet per second squared. After 1 second, the velocity will be 9.81 meter per second, or 32.2 feet per second. The distance s that the object will fall from rest in t seconds is 1/2 gt squared. After 1 second, the object will fall 4.9 meters, or 16.1 feet. If the object falls a distance or height s from rest, this occurs in time t equals square root of 2s over g, with final velocity v equals square root of 2sg. If the acceleration g on another planet were 4 times that of Earth, then an object's fall time from the same height would be 1/2 there, and the velocity reached would be double there versus on Earth. I will explain weight later, but for now, an object's weight is equal to its mass times the local surface gravitational acceleration. Weight W equals mg. So an object's weight on different planets is proportional to the local value of g. I want to give you a good feel for the acceleration of gravity on Earth, on different planets, and the Sun, and also how your weight changes with the local gravitational acceleration. Let's drop some cannonballs off the famous Leaning Tower of Pisa. The link to this simulation is available in the lecture script PDF. Let's drop one cannonball every second from a height of 50 meters, about 164 feet. Gravitational acceleration at the Earth's surface is 9.8 meters per second squared. Cannonball speed will increase by 9.8 meters per second for every second of fall. This is constant acceleration. We can ignore the effect of air resistance. We're dropping cannonballs, not feathers. While the cannonball is still falling, t seconds after we release it, its instantaneous speed will be 9.8 times t meters per second. Under constant acceleration, its speed increased linearly from 0 at rest to this value, so its average speed will have been half as much as the instantaneous speed, or 4.9 times t meters per second. It has fallen 4 t seconds at average speed 4.9 t, so the distance it has fallen is the product of those two values, or 4.9 times t squared. Each cannonball will hit the ground 3.2 seconds after we release it, because 4.9 times 3.2 squared is 50 meters. 3 other cannonballs will still be falling as we release each new cannonball every second. Before it hits the ground, its instantaneous speed is 9.8 meters per second squared times 3.2 seconds, or 31 meters per second. Pretty fast. Notice that there are 3 cannonballs in flight at any time. Notice that the distance between 2 falling cannonballs increases over time until one hits the ground. This is because the ball we released first has been falling longer and has acquired more speed than the one we dropped second. This is acceleration. Okay, good, but what about gravity on other planets? Surface gravitational acceleration is proportional to a planet's average density times its radius. Mars's average density is about 71% of Earth's. Presumably it has less of an iron core, and its radius is about 53% of Earth's. So Mars's surface gravity is about 3.7 meters per second squared, or 38% of Earth's surface gravity. An astronaut on Mars wearing their spacesuit would weigh 38% of what they weigh on Earth wearing the spacesuit. A cannonball dropped from 50 meters above Mars's surface falls more slowly than on Earth. Can you see that the cannonballs fall more slowly on Mars than Earth? Each cannonball will hit the ground 5.2 seconds after we release it versus 3.2 seconds for Earth. 5 other cannonballs will still be falling as we release each new cannonball every second. Before it hits the ground, its speed will be 19 meters per second versus 31 meters per second for Earth. Can you see in the demo that the speed hitting the Earth is faster than the speed hitting Mars? The distance between successive cannonballs increases faster on Earth than on Mars. Good. Now, what about Jupiter? Jupiter is a gas giant. We see an outer cold cloud layer, not an inner solid layer. Let's imagine that an advanced civilization has built a rigid shell around the planet at the radius of the visible top of the cloud layer, and that our astronaut is standing on the shell. He is a shell observer. We will also use this concept for stars and black holes. Jupiter's average density is about 24% of Earth's, and its radius is about 11 times Earth's. Jupiter's shell surface gravity is about 2.6 times Earth's surface gravity. A cannonball dropped from 50 meters higher than our imagined shell falls faster than on Earth. Each cannonball will hit the shell 2 seconds after we release it, versus 3.2 seconds for Earth. Here is Jupiter. The balls are accelerating faster. They hit the ground faster. There are fewer balls in flight at any moment. Before it hits the ground, its speed is 52 meters per second versus 31 meters per second for Earth. In the demo, can you see that the gravitational acceleration and speed hitting the ground are higher on Jupiter and less on Mars? In this simulation, the planets are in order left to right by decreasing surface gravity, not their distance from the Sun. Great. Now what about the Sun and the Moon? The Sun average density is about 26% of Earth's, and its radius is about 109 times Earth's. The shell surface gravity of the Sun is 28 times Earth's. Our simplified virtual cannonball falls 50 meters in 0.6 seconds, and it hits the imagined shell at 166 meters per second. The Moon's surface gravity is 17% of Earth's. Our cannonball falls 50 meters in 7.9 seconds and hits the surface at 13 meters per second. The asteroid Ceres surface gravity is 2.8% of Earth's. Our cannonball falls 50 meters in 19 seconds, and it hits the surface at 5.2 meters per second. If we were to fall 50 meters on Ceres, we could probably land pretty safely with a little care. It would be like falling 1.4 meters on Earth. We could jump pretty high there too if our spacesuit were flexible. In the demo, can you see how gravitational acceleration and speed hitting the ground vary from the massive Sun to tiny Ceres? For all these solar system bodies, the nature and mathematics of gravitational acceleration are the same, but the value for surface gravitational acceleration is 1,000 times higher for the Sun than for Ceres. Here is a different representation of the sizes of the planets. I will provide the following chart in the lecture notes. The chart gives the planets and the Sun, their masses, their radius, their average density, surface acceleration, time to fall, and velocity. Note that this demo did not indicate the weight or mass of the cannonballs that we dropped. The gravitational acceleration does not depend on the mass of the accelerating object, and we ignored air resistance. We also ignored the Sun's radiation and solar wind, and we imagined a shell around Jupiter and the Sun. Instead of a shell, we could have had the astronaut in a rocket ship, thrusting against gravity to maintain a stationary position. The astronaut's weight inside the ship would be the same as for being a shell observer. Let's look at a different simulation showing all the planets. In this simulation, a single ball is dropped from 1 kilometer. We see how slow the ball falls on the Moon, Pluto, and Ceres. Let's see that one more time. Jupiter, Saturn, Uranus, and Neptune aren't really much faster than the Earth, and Venus is a little slower. Mars and Mercury are a little slower. And then we get the Moon. Weight. As we stand still on the surface of the Earth or sit stationary, not falling toward the center of the Earth, we have weight. We are not weightless. We perceive that there is a gravitational force pulling us downward. Perhaps you feel your weight at your feet when your feet are tired, or you feel your weight in your lower back. Let's go back to Newton's law, F equals ma, when the acceleration is 0 and we are not accelerating. Our body is still gravitationally attracted to the Earth's mass, but we're not accelerating. So the gravitational force must be exactly balanced by some other force, a contact force that the floor or ground is applying to our feet. Physics students use this simplified abstract picture. So the force of our weight, shown here, downward, equals mass times gravitational acceleration g, as we said earlier, and our weight on different planets is proportional to their value for gravitational acceleration g. And while we're standing, that force is balanced by a contact force from the floor. More realistically, if we're not accelerating, then at every point in our body, gravitational force downward is exactly balanced by equal and opposite upward force due to contact with the floor, or compression of our skeleton, or tension in our arms, more like the following drawing. There are a number of interesting issues about weight on Earth. How does weight change based on where you are on Earth? Altitude, latitude, surrounded by air or water, buoyancy. How much is the force on a scale? How much does the atmosphere weigh? How much do you weigh while moving in an elevator? Why do you get hurt or die when you fall? How can you become weightless on Earth? How much is gravity inside the Earth? These issues are interesting, but our time is limited and we want to get to black holes, so I'm providing this material in a 20-minute supplementary video. We will not cover walking and running, but you might want to think about how your center of mass moves as you walk or run. We looked at dropping balls on Earth and the planets and weight while standing on Earth and the planets. Later we will look at circular orbits. Now we will look at the Sun and other stars. Life on Earth evolved in Earth's 1G gravitational field. Humans, some animals, and plants can adapt tolerably well to weightlessness, 0G, such as on the International Space Station in low Earth orbit. However, we're limited in how much acceleration or weight our bodies can tolerate and survive. Our heart and circulatory system evolved to pump in 1G. In high Gs, blood cannot reach the brain, and we pass out. If this condition persists, we die. Jet fighter pilots wear pressure suits to force blood to the brain instead of pooling in the legs. Fighter pilots in pressure suits can survive brief periods of 9 Gs, but not continuous exposure. Astronauts only experience about 3 Gs during rocket launch, and they wear pressure suits and they lie perpendicular to the direction of acceleration. The surface gravitational acceleration of the Sun is 28 Gs. Even with some advanced pressure suit, a human probably cannot survive the 28 Gs of being a shell observer at the surface of the Sun, much less the denser stars that we look at next. There are stars less massive than the Sun and stars hundreds of times more massive. Let's look at gravitational acceleration and weight for a shell observer at the shell surfaces of stars much denser and more compact than the Sun, and then some black holes. I will provide the following chart in the lecture notes. Surface gravitational acceleration is proportional to average density times radius. Sirius B is a white dwarf stellar core remnant with mass equal to the Sun, but the size of the Earth. Its average density is 2 million times that of the Sun, and its surface gravity is 14,000 times that of the Sun. A human shell observer cannot survive at that distance. The white dwarf sustains its immense core pressure via electron degeneracy pressure, that 2 electrons cannot have the same quantum numbers. But you won't need to know that for this course. The next column is for a typical neutron star. It has 1.4 times the mass of the Sun, in only 10-kilometer radius. It is the collapsed core of a massive supergiant star that went supernova. The core had enough mass that electron degeneracy pressure was insufficient to halt the collapse. All the protons and electrons combined to form neutrons, and neutron degeneracy pressure stops further collapse. Two neutrons cannot have the same quantum numbers. You don't need to know that for this class. The entire neutron star has the density of heavy nuclei on Earth. $500 trillion times denser than the Sun. Using Newtonian gravitation, the surface gravitational acceleration would be 7 billion times that of the Sun. But it turns out that this density is high enough that we should use results from Einstein's general relativity, not Newtonian gravitation. Before we calculate the correction to surface gravitational acceleration from general relativity, we need to calculate the gravitational radius, the Schwarzchild radius, from the mass using this formula. The Schwarzschild radius, r sub s, is 2 gm over the speed of light squared. For the Sun, that would be 3 kilometers. So for any object, its Schwarzschild radius is 3 kilometers times its mass divided by the mass of the Sun. Now some texts and some graphs use 2m to mean the Schwarzschild radius, and they just leave out g over c squared. We won't do that in this course, but if you were comparing to some other source, you could be confused if you just see 2m. For the Sun and the white dwarf, the Schwarzschild radius is 3 kilometers. For the neutron star, we get a Schwarzschild radius of 4.1 kilometers. Smaller than the neutron star's radius of 10 kilometers, but not by much. If the density of neutron stars were 15 times higher, they would be black holes, but they aren't. A mass's Schwarzschild radius is important in that it distinguishes black holes from ordinary objects. It indicates how close you can get to a black hole before spiraling in, and all the formulas that tell us how time, space, and acceleration behave near a black hole or other compact, dense object use the Schwarzschild radius of the object's mass. This formula is the general relativity correction factor relative to classical Newtonian value to the gravitational acceleration and weight observed specifically by a shell observer. Not a plunging observer, not an orbiting observer. Outside a non-rotating spherically symmetrical mass, whether a black hole, an ordinary star, a planet, a moon, etc. The correction factor is infinite at the Schwarzschild radius. If r were r sub s, this would be 1, 1 minus 1 would be 0, and 1 over the square root of 0 would be infinite. So the correction factor is infinite at the Schwarzschild radius, which is shown here. The Schwarzschild radius is the dotted red vertical line, and as we approach it, the correction factor gets to be infinite. But as we move away from it at increasing distance, the correction factor falls rapidly. And it can be ignored beyond about 50 Schwarzschild radius, and at infinite distance, the correction factor just becomes 1. This general relativity correction factor is 1.31 at the surface of the neutron star. 1.0003 at the surface of the white dwarf, and very close to 1 at the surface of the Sun. Because of this, the gravitational acceleration that an imaginary shell observer would experience at the surface of the neutron star is actually 9 billion times stronger than for the Sun, versus 7 billion predicted by Newton. The general relativity correction factor for the weight of a shell observer is negligible at the surface of the Sun. However, the correction for the orbit of Mercury is very small, but measurable and verifiable. Suppose the Sun could contract all its mass to become a black hole. This can't really happen, but just suppose we woke up one morning and the Sun was collapsed into a black hole. What would happen to the orbits of the planets? Would the planets be sucked into the black hole by virtue of it being a black hole? It turns out the orbits of the planets would be unchanged.